In this video, we'll turn to the general linear model, which allows us to analyze more complex experimental designs. These are obviously much more common, especially in recent times, because they allow us to ask more interesting experimental questions about the neural correlates of more complex behaviors. So they're common in neuroeconomics. So we've discussed the condition that's shown at the top here, which are fine to be analyzed via, let's say, a t-test or correlation analysis. But we have a simple design with one treatment condition, which I called condition A here, versus a control condition. So we can then construct these types of time courses, let's say in a correlation analysis, that model the expected bold response, the predicted bold response, given our experimental design, so the onset and offset of task conditions, and the onset and offset of control conditions. And we can check whether there's a correlation, obviously after convolution, which I left out here, between the observed signal and the predicted signal. This would be a simple correlation analysis, which is actually a special case of the general linear model. But we want to extend this to designs where we have multiple conditions. Let's say condition A versus condition B versus some control condition. And condition A and B are indicated here by the blue and green convolved predicted responses. So this would be a time series that we could expect in some cases for still simple but more complex designs that would no longer allow us to just perform simple correlation analysis. So to summarize this, t-tests are adequate when we compare two conditions, and they don't fully capture the slow time course of the fMRI response. Correlation analyses can help in this latter respect, so we capture the slow time course of the fMRI response, but they're also just designed to compare two conditions. And what we want to do is we want to be able to analyze and conduct more complex experiments, so we need to generalize to n arbitrary conditions. A strategy is to employ a general formalism here, namely multiple linear regression, which you have learned about in your econometrics course or your introductory statistics courses. So let's consider the general linear model in a little bit more detail. What we're doing basically is we're looking at explaining the changes in our dependent variable as a function of multiple factors that might affect this dependent variable. So in our case, y sub I here is the dependent variable. That's what we're observing, what we're measuring in fMRI is the bold response within each voxel. Within each voxel is stressed here because we're basically conducting this analysis across all the different voxels in the brain that we record from. And that's typically in the order of 100 to 200,000. Then the x sub 0 here is the effect of constant factors. So the contributions of constants, it's our intercept, as you might know it better from behavioral data analyses. This is, in our case, for instance, one contribution or one contributor to this effect is the T2 star effect activity during no task. And the beta 0 then is the intercept parameter. Then we have multiple other regressors that we're adding into this model specification here. So we may have condition A, we may have condition B, and we may have a control condition as well. So we have three regressors that we're interested in. But typically we also have a number of nuisance regressors in a model like this. And in our case, when it comes to analyzing fMRI data, such nuisance regressors might be the motion parameters that we add to this model. Then we have other randomly varying factors that we're not including and that go into the noise term or the error term, the residual term, basically. This is all the unexplained variation. And a model then is estimated using a least squares approach. One of the important things to consider, and the aspect that makes this a general linear model, and I'll show this in the next figure, is that these x's here contain multiple time points, so they contain time series across the different scans that were taken in the experiment. So they're not just single points or single predictor variables, they're time series that reflect the experimental design. So let's say when condition A was on versus off, so when participants were performing a particular task. That is what is illustrated here, for instance, right? So this is one regressor, one of these x variables, let's say x sub 1, where in condition 1 participants are performing a certain task at specific time points, so we have these time series here. And that's why we typically specify a design matrix as a vector of different regressors, so x 1 to x sub p, with a certain length, and the length represents the length of our experiment, or the number of recordings we took in the MRI. So the design matrix basically embodies all available knowledge about our experimental design, all the factors that we controlled, and all the knowledge that we have about confounds. And the confounds also go into this large array of regressors here, which include regressors of interest, such as condition A, condition B, control, as well as regressors of no interest, which we just entered to control for this, such as motion regressors. So the movement that we know the participants, that we estimated from the motion correction step during pre-processing. And all of this will then predict the bolt response in each given voxel. And this has just a length of 1 because it's just one voxel that we're predicting here. What the model then does is it estimates the beta parameters for each one of these regressors, for each one of these x sub 1 to x sub p, and it estimates an error term using linear least squares approaches. So that's our cost function, right? The least squares type cost function. So just to go over this again, so we have a design matrix X, which contains all of our regressors, and that is the reflection of all the experimentally controlled factors and all the potential confounds. N here is the number of scans, so how many scans, it's our time series, how many scans did we record. It's typically in the order of 500 to 1,000, let's say, for a typical experiment. And P is the number of regressors that we're interested in, and for each regressor, a beta value is estimated by minimizing the error term in a least squares fashion. And this is eventually what we want to specify. So as the experimenters, we only specify the design matrix, and we obviously record the bolt response to our experiment. Just to go over this in more detail, this is how a design matrix looks like. This is a relatively simple design matrix in SPM, but it can be subdivided into different parts. This is the kind of output you get when you specify your experiments, when you specify your regressors in SPM. We have the experimental factors, which are shown here in orange. They are the explicit manipulations that you introduced in your experiments. So this is when you know participant is performing a particular task versus some other task. So this could be, for instance, when the participant is attending to some conditions versus when he or she is not attending to some conditions. It could be correct versus incorrect trials. You could also enter reaction times as a continuous regressor in there. So anything that you know and that you observe and that you manipulate can go in there. We also have a set of nuisance factors, which are shown in blue here. And those include the scanner drift. If you recorded or estimated it, you can also add physiological noise. But you can also add motion parameters that were estimated during the pre-processing step, especially, the pre-processing step that performed motion correction. That in SPM gives us an output that allows us to then later control for these types of motion parameters. And they are referred to here as R1 through R6. And you can see that they're a little bit smoother than the regressors that you specify based on the experimental design. So here's a brief illustration of what the general linear model then does. Basically, It tries to explain the variability in y by a weighted sum of all the factors or regressors that are entered into your model. These factors include experimental factors, so regressors that reflect conditions of interest, such as treatment and control, but also nuisance factors, so factors that may also contribute to signal changes, such as motion parameters, right? That we record and estimate. These are hypothesized components of the signal y, but they may in fact not contribute, may or may not contribute to the changes in y. And this is something that we want to estimate. So what the general linear model then does is it adjusts the weights, the parameters, beta 0 to beta 1 to beta p, to minimize this error term. So the best combination of these parameters is estimated in statistical analyses to identify the ideal contributions of our hypothesized predictors or regressors, these x here, these x components, in terms of how much of the variability in y they explain. So SPM calculates what combination of beta weights, when multiplied by these factors here, which are indicated by x, provides the smallest error term. And a common approach to do this is to simply minimize the sum of the squared residuals of this model. I'd like to finish this video by reminding you that when we model something, then we're basically abstracting reality. So a model is a sparse representation of reality, just like shown in this image here. So the model here on the right is basically what we can accomplish using our general linear model, whereas the data, in fact, would look much more, or the reality which would look much more like this. But it is useful to model aspects and relationships between different variables that we can measure and manipulate, because it gives us insights into how different aspects play out, and it gives us insights about the mechanisms of the brain or the neural correlates of certain behaviors. But it's a good reminder to see our general linear models as, well, simplifications of reality that might look more like this stick figure here, whereas reality might be much more complex. So we make the assumption when we model that our model is an adequate representation of reality. It's good practice, therefore, to really, before you start your experiment, consider and think carefully about your model that you run before you run the experiment.